going to start the recording a little bit early. Did y'all get the email last night about no spring break? Thoughts on that? Yep. But hey, compensation, you get more reading days, right? That the compensation we're all looking for here? Okay. Try to match that. There we go. Quiz 2. Okay. Alright, so just a couple quick announcements. So quiz 2, like I've been saying, covers lessons 4, 5, and 6. And it's today at 9 a.m., so in about 30 minutes, to Thursday at 9 a.m. So tomorrow. Quiz 3, I think, check Piazza for this, but I think they said it's Monday from 9 a.m. to Tuesday at 9 a.m., if I recall correctly. And then it's going to be on lessons 7 and 8, I believe. Okay. And, okay, here we go. Zoom office hours. So, just out of sheer curiosity, just show of hands, who tried to get into Zoom office hours on Monday? Okay, I know you did. Anyone else? Okay. Alright, so, for those watching online, I owe you guys a little bit of an apology, because, I realized I was on the wrong channel last time, so for those that want to get into Zoom office hours tonight, now that I know I screwed up, I'll make sure to be on the right channel tonight. So just, for those that are looking to get some office hours in tonight, so that way you guys know I'll be in the right channel this time. So, okay. Any other questions on anything? Any homework questions that you would like to discuss? Okay. So, let's talk about instantaneous rates of change, and specifically, its applications to derivatives. So, recall last time, / on Friday, for a function f of x, the slope of the secant line between x equals a and x equals a plus h is, well, m equals f of, well, I'll write this as f of x minus f of a, divided by x minus a, and then we also have the other way of writing it, which was the difference quotient, which is equal to f of a plus h minus f of a, all that divided by h. So essentially, these are essentially two different ways of expressing the same thing here. And in terms of applications, this is also known as the average rate of change from a to a plus h. Okay? So the slope of the tangent line, meanwhile, at x equals a, was the limits definition, what we had from Wednesday, oh, not Wednesday, Friday, was that we take the difference quotient here, and then we just let h go to 0. So we have f of a plus h minus f of a all over h. Okay. Now in terms of applications, this is also a rate of change, but in this case, this is going to be referred to as an instantaneous rate of change. Instantaneous rate of change. Okay. All right. So to see what I mean by this, well, let's take a look at example 1 here. So let s of t be this quadratic, t squared minus 2t plus 3, and let that be the position of the car in meters after t seconds. So in this case, first thing we have to do is find the average velocity over the first 5 seconds. Okay? So for part A, oh great. Well, that happened. All right. Well, we're just going to have to improvise and use a pen. Hopefully, I don't write too many scribbles. All right. It's going to be a fun day. Here we go. All right. Okay. So, part A. Recall. So, if you recall from high school physics, or whichever class you may have seen this in, so velocity is equal to, well, it's equal to displacement over time. If you remember that from high school. So, remember, displacement was in meters, and time was in seconds. So that ultimately means that your velocity is going to be in meters over seconds. Okay? So, since we're finding the average velocity over the first 5 seconds, that should mean we need to focus on what 2 values of t here. So in this context, we're saying if we're focusing on the position after t seconds, that means usually implicitly means we're going to have t greater than or equal to 0. Okay? So if we're trying to figure out the average velocity over the first 5 seconds, then what that means is that we'll need to focus on what 2 values of t here.
0 and 5.
0 and 5, right? So that means for time, we're going to be focusing on, the difference between 5 and 0, because that's going to be our difference in time here. So then regarding displacement, what do you think we'll need to focus on here? So in this case, displacement is going to be, well, the change in, position from t equals 0 to t equals 5. So what quantity do you think we'll need to use to express that? Change in displacement from, in this case, t equals 0 to t equals 5. So what two quantities are we going to need to subtract here?
The position at 5 and the position at 0.
Right, so s of 5 minus s of 0 is going to be our displacement here. Okay? So, from this we say, all right, well, we already know what the denominator is, that's just 5. So now all we need to do is figure out s of 5 and s of 0. So all we need to do is just let t equals 5 and t equals 0 in our position function up here. So if we let t equals 5, then what should we end up with as our position at that time?
$18.
18, right? Yeah, 18, because you end up with 25 minus 10 plus 3, which that's just 18. Okay? And then meanwhile, if you let t equal 0 in this, you should pretty quickly end up with what?
3.
Yeah, just 3. Okay? So you simplify the numerator as much as you can. You should end up with, well, 15 over 5. And so you should pretty quickly get that this is just 3 meters per second. So that will be your average velocity in this case. So any questions on that? Okay. All right, so let's move on to page 2. Okay, so page 2, we're just going to be sort of continuing on from example 1. So in this case, part B, we need to find the instantaneous velocity at t equals 2. So in this case, to get instantaneous velocity, which will we need to do here? So in this case, if you recall from part A, to get the average velocity, we just had to take the displacement over time over a specific time interval. So now if we want to figure out the instantaneous velocity, based on the setup that we had at the start of class, what do you think we'll need to do with our position function here?
Take the derivative of it.
Right. So in this case, we'll need the limit as h goes to 0 of s of t plus h minus s of t all over h. And that's going to not only correspond to the derivative of your position function, but that's also going to correspond exactly to your velocity function, which I'm going to denote by v of t. Velocity at time t. So make sure to keep this relationship in mind for future examples. So if that's the case, we say, all right, well, first off, well, what is v of t then? So if v of t is just the derivative of position, then taking the derivative of our given position function is just what? So if we take the derivative with respect to t of our quadratic, what should we end up with?
T minus 2.
Yeah, just 2t minus 2, right? Just a quick little application of power rule in this case. Okay? And so the nice thing is that as with average velocity, instantaneous velocity also carries the same units as before, namely meters over seconds. Okay? So that means that if we're trying to find the instantaneous velocity at time t equals 2, well, all we have to do is just, well, let t equal 2 to get v of 2, which is simply what? So v of 2 would just be
2.
just 2, right? Because you just have 2 times 2 is 2, and that's just 2. And again, that's in meters per seconds. Okay? All right. So now with part C, we need to figure out when the car's instantaneous velocity is equal to 0. And at what position is the car in at that time. Okay? So with part C, so let me just do this. Okay, so part C, we're trying to figure out what time is the velocity going to be 0 here. So what does that mean we need to do about our velocity? We need to take v of t and then do what with it?
Set it equal to 0 and then solve for t.
Yep, just set it equal to 0, right? because we're trying to figure out at what time t is the velocity equal to 0. So we have 2t minus 2 equals 0. So from that, you should pretty quickly get that t, which should equal 1. Yeah, just 1, right? Equals 1 second. Okay, so that's good and all, but that's only half the problem, right? Because now we know when the car's instantaneous velocity is 0, but we need to figure out what position is the car in at that time. So now we need to take t equals 1 second and then do what with it?
Plug it into the original.
Yep, we got to plug it back into the original function. So we have s of 1 is going to give us the desired position. So we just let t equal 1. So we get 1 squared minus 2 times 1 plus 3. And then so from that, you should pretty quickly get that the position at that time is going to simply be 2 meters. Okay? Okay, so that's that one. So any questions on that? Alright. Okay, so that's all I wanted to say on that example. So let's move on to example 2. So if you recall from high school geometry, the volume in this case, cubic meters, of a sphere in terms of its radius r in meters is given by v equals 4/3 pi r cubed. So the goal now is we need to figure out the rate of change of the volume with respect to the radius r when r equals 1. Okay? So one thing to keep in mind is that if the homework just asks for rate of change, it doesn't specify average or instantaneous, just assume it wants the instantaneous rate of change. So instantaneous rate of change. Okay. So just assume it wants you to figure out what this is. Okay. And one more thing to keep in mind is that, as I sort of brought up in the previous example, so also for y equals f of x, or whatever your variables are in this case, units of f prime of x are going to end up being what? So if you recall, we have one way to express the derivative is that we have f prime of x is the same thing as dy over dx. Okay? So in this case, we say, all right, well, we're having something involving y over something involving x. So in this case, that means that the numerator here is going to carry the same units as y does, and the denominator is going to carry the same units as x does. So essentially, we have units of y divided by units of x. Or again, whatever the appropriate variables are in the context of the problem. So in the context of problem 1, you had the units of position, meters, divided by the units of time, seconds. So just a nice little thing to keep in mind for problems like this. So, okay. So with that in mind, we're given v of r in this case is just 4/3 pi r cubed. So in this case, if it wants the rate of change of the volume with respect to r, in this case, if we're assuming instantaneous rate of change here, that means we need to figure out, first, find, in this case, the rate of change of volume with respect to the radius r. Okay? So if that's the case, we say, all right, well, and before we move on to what the derivative itself is, what would the units of this be based on our above remark? So in this case, our y variable is in this case the volume, and our x variable is the radius.
Meters squared?
Right idea, but we don't want to simplify it quite to that.
Oh, so meters cubed over meters.
Yeah, just in this case, you want meters cubed over meters. So, because in this case, the rate of change is basically saying you want the rate of change of cubic meters per meter, essentially. So that's the idea behind that. Okay. So now let's go ahead and find dV dr. Okay. So dV dr is going to be, well, if we use sort of the same notation that we did last time, then we can just express this as the derivative of 4/3 pi r cubed with respect to r. So if we take the derivative of this as we did last time, what should we end up with? Yep, just 4 pi r squared, right? Because if you take the constant out, in this case 4/3 pi, then you should end up with 4/3 pi times the derivative of r cubed with respect to r. And if you apply power rule on this, well, you should just end up with 4/3 times pi times 3r squared. So that means the 3's will cancel each other out, and you are just simply left with 4 pi r squared. Okay? So this will correspond to your derivative of velocity. Not velocity, volume, sorry. My bad. Gotten used to seeing V so many times. So, if that's the case, we say, alright, well, now we have the rate of change of volume with respect to the radius r, as given by this equation right here. So now, we need to figure out what that is when r equals 1. So, all we have to do now is just say, alright, if r equals 1, then just let r equal 1 right here to get v prime of 1 should, well, if you just let r equal 1, you should pretty quickly see that. So that's just 4 pi. Okay? Okay, so that's not too hard to see in terms of the quantity. So now let's get a better idea of what that means in terms of trying to write that as a complete sentence. So one thing to note here is that v prime of 1 is equal to 4 pi. But this is just a positive number, right? So this is greater than 0. So because it's positive, that means that your volume is going to increase. So derivative greater than 0 implies, or that directly corresponds to volume increases. Okay. So because of that, to write this out as a physical sentence, we say, all right, when r equals 1, v increases at a rate of 4 pi cubic meters per meter with respect to r. So if you want a physical complete sentence in terms of what we just computed, this would be your way to do it. Okay. Now, it's not something you'll need to do on the homework, but it's just something good to know if you ever get asked that and say, and if you ever like have a family member that's like, cool, what are you doing? I'm doing calculus. Cool. What does all this mean? Well, here's a way you can explain it. You ever have family member that's, or just a friend that's asking, what am I doing with this calculus stuff? So, okay. Any questions on that? All right. So some of you may have noticed, for example 3, I decided to get a little creative with some of my examples. So what I'm going to do is this. So, all right. So for example 3, Nintendo estimates that the amount of money it spends to maintain Smash Bros. Servers is given by this quadratic right here. C of t equals 200 t squared minus 100 t plus 60,000, where t is the number of months after January 2019. You can assume the servers went live then for the sake of simplicity. Represents maintenance costs in thousands of dollars at time t. Okay. So first off, we need to figure out the rate of change of the cost 1.5 years after the servers go live. So, if we need to find rate of change, as usual, that's a good enough indication that we need to find the derivative. So, first, find c prime of t. So if we take the derivative of our cost with respect to the only variable we have, t, then what should we end up with as our derivative here?
Minus 100.
Yep, just 400t minus 100. Just a quick little application of power. Okay. So that'll give us the rate of change at any time t. Okay. So applying that to part A, we're trying to figure out the rate of change of the cost 1.5 years after the servers go live. So what should that tell us about what we need to plug into t here? What we need to plug into our cost function. Let's give someone else a chance. So what do we need to plug in as our t value here?
So it would have to be 18 months.
Exactly. So yeah, remember, be careful with the units here. So t is the number of months after January 2019, and we're trying to figure out what happens 1.5 years after that. So 1.5 years is the same thing as 18 months. So in this case, that means we need to plug in t equals 18 into our derivative function. Okay? So we have 400 times 18 minus 100. So that'll end us up with what as our derivative value? You can use a calculator if you need to. Yep, just 7,100, right? All right. So in this case, if we were to write this out as another complete sentence, then we say, all right, well, interpretation. Well, since our derivative is 0, that says the rate of change of maintenance costs, rate of change of maintenance costs, 1.5 years, 1.5 years after servers go live increases at a rate of what? So in this case, since we have 7100 as our derivative value, what should that tell us about the quantity as well as the units? So it increases at a rate of what? So in this case, so 7100 will correspond to, so remember, C of t represents maintenance costs in thousands of dollars. So what would that tell us about the quantity that we're going to end up using here? So this is in thousands of dollars, right? So then that means that 7100, so this 7100 here will give us that so this is thousands of dollars, so that means how many dollars would this correspond to? If this is in thousands of dollars.
7.1 million.
Yep, 7.1 million, or 7,100,000. Okay. So this is in dollars, but then because this is the derivative, we say, all right, well that's the units of cost, but then we need to divide that by the units of our variable t here. So that means that this is going to be $7,100,000 per month, because this is the units of our x or t variable here. Okay. Okay. So that's part A. So any questions on that? So for part B, we need to figure out at what month will maintenance costs increase at a rate of $2,300,000 per month. So that means we need to, what do we need to do with our derivative? Okay. So that says, when will maintenance costs increase? So that means we need to take our derivative function, c prime of t, and set it equal to what?
2300.
Yep, 2300, right? So that's going to be our equation we need to solve here. So we have 400t minus 100 equals 2300. So then do a quick little bit of algebra to get that t equals what? So t should equal what nice number? Yeah, just 6, right? So in this case, that'll correspond to 6 months after the servers go live in January 2019. So what month should that correspond to? This corresponds to 6 months after January 2019. So what month should we get from that? July, right. 2019 is the desired answer here, because that is 6 months after January 2019. Okay. So any questions on that? So I'll give you guys a second to write that down, and we'll move on to the next example. Okay. Okay. Anyone still copying down example 3? Okay. All right, we'll go on that time. so for example 4, two variables p and q are related by p equals 3q minus 5. So for part A, we need to figure out the rate of change of p with respect to q. So if we look at this relationship here, we have p equals 3q minus 5. So the good news is that this says that p is already in terms of q. So for part A, we're trying to figure out the rate of change of p with respect to q, right? So what should that tell us about our derivative here? So in this case, what this sentence here is saying is that we have p of q as a, so we have p as a function of q is 3q minus 5. So what that says is that, all right, if we're trying to find the rate of change of p with respect to q, then that's saying that all we need to do is find the derivative of p with respect to q. So that's all that question's there is asking. So if that's the case, well, one can pretty quickly see that if we take the derivative of our p variable with respect to q, we should pretty quickly see that that derivative is what? Yeah, just 3. Just take the derivative of this function with respect to q, and then you should get 3. So to lay that out a bit more clearly, just take the derivative of this with respect to q, and you should end up with 3. Okay? So now for part B, it's going to be a similar idea, except the roles of q and p are now reversed. So in this case, what quantity are we trying to find here? We're trying to find the rate of change of q with respect to p, and that means what does that tell us about our derivative? So we need d over d what over d what?
Q over P.
Yeah, q over p. So because of that, well, wait a minute, we only have p equals 3q minus 5, right? So that means what that tells us is that we should probably find some way to get q in terms of p, right? So if we were to do that, that means we need to get q by itself, is what that's saying. So if we have p equals 3q minus 5, that means we need to solve for q. So if we were to do that, then what should we get as q here? So q should be equal to what? What's that? Plus 5 over what? Yeah. So that means that we have q equals p plus 5 divided by 3. So that's good. But what we're going to do is we're going to actually rewrite this a little bit differently. So what I'm going to do is I'm going to say, all right, since these two, this p plus 5 have common denominators, what I'm going to do is I'm going to rewrite this as p plus 3 plus 5/3. And the reason we have that is because then we can say, all right, well, not only do we have q in terms of p, but then if we were to rewrite or then if we were to take the derivative of q with respect to p, that should tell us our derivative is then what?
Third.
Yeah, just third, right? Because then this is just saying we have d over dp of dp over 3 plus 5/3, and that's just, well, 1/3. Okay? So that's all example 4 is saying. So any questions on that? So that's all the homework questions I wanted to talk about, but there's one other problem I wanted to take a look at, and the reason for that is because that's one of the problems that you're likely going to end up seeing on the review problem packet for example 1. Yeah?
I was just curious, like I noticed that it's 3 and 1/3. Does it being the inverse of the other ones, is that like a common trend for that? Or maybe
like in this particular case?
yeah, so like if you're finding with 2 variables, is it common that it's the inverse of the other?
Generally no, but I think it only plays nice in this case because you have p in terms of q as a linear relationship. If you have like a quadratic or anything else, it's probably going to end up being no. So does that answer your question?
Yeah.
Okay. Okay. So any other questions on that? Okay. So this next one is going to focus more on an application that you'll see as something you'll see in the exam 1 review packets. So I'll go over that. So example 5, suppose we have a ball thrown off the top of a 240-foot tall building. The height of the ball above the ground t seconds after being launched is expressed by this quadratic here. So first off, we need to find the velocity of the ball as it hits the ground, and we need to find the maximum height of the ball. Okay? So let's draw a diagram to see what's going on here. So here's the ground. This is at h equals 0. So let's say our building is right here. This is going to be at height equals 240. Okay? And let's say someone launches the ball off the top of the building, and because our height is expressed as a quadratic with a negative leading coefficient, that should tell us that our trajectory here is going to end up being a parabola that's downward facing. So that tells us our trajectory of height is a downward facing parabola here. Okay? So in this case, we're saying, all right, for A, we need to find the velocity of the ball as it hits the ground. So in this case, we're saying, all right, well, so the ball hits ground when what happens? So if we take a look at our picture here, we have the top of the building is 240, and the ground corresponds directly to h equals 0. So based off of that, that says the ball hits the ground when h equals 0. So what should that tell us about what we need to solve for here? We need to solve h of t equals 0, right? So that will give us the precise time that the ball hits the ground. Okay? So if we were to do that, we say, all right, well, set our quadratic here equal to 0. So we have negative 16t squared plus 32t plus 240. So to make things a little bit easier on our end here, what we're going to do is we're going to factor out this negative 16 here, so that way we can see a bit easier how to simplify the quadratic. So we have negative 16. So if we factor out negative 16, we have t squared. And then, well, you can pretty quickly see that this is just 2t as the middle term. but then the coefficient or the constant term should be what if we factor out negative 16? You can use a calculator here. Yep, negative 15. Good. Okay. So we have negative 16. So if we take this form of the quadratic into account here, that means we should be able to factor this as what two things?
Negative 5
Yep. T minus 5 and t plus 3. Okay. So if we set this equal to 0, that should give us two values of t from this. So we get t equals negative 3 and t equals 5. But remember, as we had with example 1, we're only allowed to have t greater than 0 because t equals 0, it corresponds to the split second the ball gets launched off the building. So, but only t greater than 0 allowed. So because of that, we only need to focus on t equals 5 here. Okay? So that'll give us the time when the ball hits the ground, but now we need to find the corresponding velocity. So since we need velocity, so remember from example 1, if we need to find the velocity, it seems like we need to take our height function and then do what with it? Find the derivative, right? So v of t equals the derivative of height, which corresponds, so if we take the derivative, we should get what out of this? Yep.
Negative 32t plus 32.
Yep, negative 32t plus 32. So then that'll tell us that the velocity at time t equals 5 is just h prime at 5, which, if you let t equal 5 in here, you should get that this is 128, in this case, feet per second, because our units of height are in feet now. Okay? Alright, so that's part A. Now part B. So for part B, we need to find the maximum height of the ball. So let's take a look back at our picture here and see what's happening with this. So maximum height of the ball, if we take a look at this, that looks like it's going to correspond to right here, right? So let's draw a tangent line around that point and see what happens. So if we draw a tangent line at that point, well, what do we notice? So it looks like this is just a flat horizontal line, right? But flat horizontal lines have what? Have slope what?
0.
Slope 0, right? So that means that since the slope of the tangent line corresponds to the derivative, well, that means we need to be setting the derivative equal to 0 here, right? So consider tangent line at max height. The line has slope equal to 0. So if that's the case, that means that we should be taking our derivative and setting it equal to 0 here, right? So if that's the case, we say, all right, well, negative 32t plus 32 equaling 0, since the slope of the tangent line corresponds to our derivative. So you can, if we solve for t here, one can pretty quickly see that t should equal what here? T equals what?
32.
T equals 32? 1. There we go. If you just solve for t here. Okay? So that'll give us the time at which we achieve maximum height. So to get the maximum height, we'd say t equals 1 and do what with it? Yep, you need plugging it back into our original height function. So in this case, we should end up with, well, negative 16 plus 32 plus 240. And that'll give us 256 as our maximum height, which is in feet. Okay. So that's example 5. Any questions on that? Alright. So that's all I have for today. So I will see you guys either in Zoom office hours tonight, which I promise I'll be on the right channel this time. I apologize for not being on there before. My bad. But otherwise, I will see you guys on Friday. I'll promise to bring a good pencil this time. Thank you. Yeah.
Have a good day.
You too. You too.